friends. In the pericyclic reactions, CHO-250, in some last lecture we have discussed about the definition of pericyclic reactions, the types of pericyclic reactions. Mainly there are 4 types of pericyclic reactions: electrocyclic reaction, cycloaddition reaction, sigmatropic rearrangement, sigmatropic reactions, and the group transfer reactions. So out of which we have discussed the first type, that is electrocyclic reaction, and analysis of electrocyclic reactions by 2 methods. In syllabus there are 2 methods only. So first method we have discussed, that correlation diagram. With the help of correlation diagram we have shown that the given reaction by counter-rotatory motion is allowed thermally or photochemically. So now second method we have to consider, that is frontier molecular orbital method. Frontier molecular orbital method, or in short this method is called FMO method. Frontier molecular orbital, FMO method. Okay, this method is called as FMO method, frontier molecular orbital method. Now this method initially we have applied for 4n pi electron system. Okay, so the simple example for 4n pi electron system, here the conversion of 1,3-butadiene to cyclobutane. Okay, simply general reaction we have to write here. And this is ring closing reaction. So the ring closing or ring opening reaction, we have to just consider the open chain partner using frontier molecular orbital method. So general reaction. In general reaction, consider open chain partner. Which is open chain partner here? This 4n pi electron system, or here simply 1,3-butadiene is a open chain partner. Okay, so open chain partner contain how many electrons? Pi electrons involved. There are total 4 pi electrons involved. So 4 orbitals are there: psi1, psi2, psi3, psi4. 2 are bonding, 2 anti-bonding, indicated by asterisk. So 4 molecular orbitals. We have to draw first orbital. So what is? Consider the system, then write general reaction, and consider open chain partner. See how many molecular orbitals involved and draw the molecular orbital. Okay, simply drawing of molecular orbital is similar. It's like correlation diagram. Psi3, psi4 star. So these are 4 orbitals. So 4 molecular orbital, there must be 4 atomic orbital. So draw 4 atomic orbital. 3 orbitals, 3 and 4. Here 4 atomic orbitals. Similarly, draw for psi3 star, and similarly again draw for psi4 star, 4th orbital. Here in correlation diagram there is need to draw both reactant as well as product orbital. But FMO method is simple than the correlation diagram, because in the manner here we have to draw only the molecular orbital of open chain partner only. Here open chain partner, no need to draw the orbitals of this product. Okay, orbital of closed chain or cyclic product. Okay, in this case similar manner we have to draw the number of nodes 0, 1, 2, 3. So no node in this case first. So give signs, plus, plus, minus, minus, minus. Here in this case, see, 1 node is there, so put symmetrically. So plus, plus, after node it becomes minus, then minus, 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 plus, plus. Here 2 nodes, plus is symmetrically, plus, after node it becomes minus, no node, minus remains same, after node sign changes, plus. So minus, after node sign changes, plus, no node, plus, after node sign changes to minus. So next 3 nodes, 1, 2, 3, plus symmetrically. So node plus, after node it becomes minus, node plus, and then again after node minus. So minus, after node know this very well in some last lectures. So M symmetric, M asymmetric. But which symmetry is present? C2 symmetric. So here C2 asymmetric. Here in this case M symmetric third and C2 asymmetric. Here M asymmetric and C2 symmetric. So alternative symmetries are present here. M symmetry, C2 symmetry, M symmetry. So total 4 electrons involved. So these electrons are filled according to the rules for filling of orbital by electrons. So what is the rule? First orbital occupy 2 electrons, and then second orbital, next higher energy orbital, occupy 2 electrons. So this is the electron, and these orbitals are empty. These orbitals are empty in ground state. So these orbitals are empty in the ground state. So when these orbitals are empty, then we have considered here ground state orbital. Okay, ground state. So this last orbital, last orbital containing electron, which is that is a CHO. So this last orbital is called as HOMO, and next to HOMO is a LUMO. So these two orbitals are important. These two notations are important in frontier molecular orbital method. What is that? HOMO and LUMO. What is that? HOMO means highest occupied. Last electrons entered into this one. So highest occupied molecular orbital, HOMO, and this one is lowest unoccupied. U for unoccupied, lowest unoccupied molecular orbital. So this is lowest unoccupied, and this is highest occupied molecular orbital. So now in electrocyclic reaction, we have to consider the highest occupied molecular orbital. Symmetry of HOMO. What is symmetry of HOMO? Symmetry of HOMO is C2. Symmetry of HOMO is C2. So see here C2 symmetry for HOMO. HOMO having C2 symmetry. How can we show C2 symmetry? C2 symmetry shown in this manner. Plus, minus, minus, plus. So this is C2 symmetry. As we take a central point, go for same distance, some distance, negative, again for same distance but in opposite direction, we get same sign. So this is C2 symmetry. So what is the symmetry of HOMO of ground state? C2. Okay, C2. So now we know that C2 symmetry, for bonding to occur, it must be by conrotatory motion. By conrotatory motion. When conrotatory motion is there, then it must give bonding molecular orbital. So bonding molecular orbital. So bonding, this one rotated in this manner, plus sign goes here, this one rotated again clockwise, then plus sign goes here, negative sign goes here, and we get bonding molecular orbital. So bonding molecular orbital. So by conrotatory motion, here when the HOMO we are considering is a ground state HOMO, when HOMO we are considering is a ground state HOMO, then the reaction must be thermally allowed. Okay, so see here again, go for selection rule. 4n pi electron system. System is a 4n pi electron system. Okay, system is a 4n pi electron system. By conrotatory motion, this reaction, conrotatory motion means C2 symmetry we have to consider. This reaction is allowed thermally because we are considering here thermal HOMO. Thermal activated HOMO, because no excitation of this orbital. Now look at the next one, that instead of this, if we consider here photochemical mode. What happens in photochemical mode? The ground state electron remains as it is. Okay, ground state orbital remains as it is, but one of the electron from this outer orbital, CHO2 excited, one electron remains here, and one of the electron goes to excited state. What is that excited state? Psi3 star, and this Psi4 remains empty. Okay, Now we have to assign HOMO and LUMO here for excited state. HOMO and LUMO for excited state. What is the HOMO and LUMO for excited state then? Which is HOMO now? Psi 3 star is HOMO. What is HOMO? Highest occupied. Now which is occupied? This one is occupied because it contains electron. Now this becomes empty, that's why it's unoccupied. This one is occupied because it contains electron, but last electron enter into this, so Psi 3 star is HOMO now. So this is HOMO, highest occupied molecular orbital, and this is LUMO. This is LUMO. Now we have to consider the HOMO, symmetry of HOMO is important for us here. So HOMO, now HOMO for excited state, HOMO for excited state is what? HOMO for excited state is Psi 3 star having which symmetry? Having Psi 3 star having M symmetry. Having M symmetry. So see here Psi 3 star M symmetry. How M symmetry? Plus, plus, minus, minus. Now M symmetry, by M symmetry, see here M symmetric orbital is there. Now M symmetry, we know that this rotation is always associated, because when we allow conrotatory motion, then what happens? Plus sign goes here and negative sign goes here. So plus minus, that overlap is a overlap will be anti-bonding overlap. But when we use this rotatory motion, so this rotatory motion we have to consider here. By this rotatory motion, one rotated clockwise, another rotated anti-clockwise. So one rotated clockwise here, another rotated anti-clockwise. One rotated clockwise and anti-clockwise, then it results into the bonding overlap. Then it results into the bonding overlap. This one rotated clockwise, so plus goes here, minus here. And when this one rotated anti-clockwise, then plus sign here and minus sign here. So it results into the bonding overlap. Bonding overlap. Okay. So what is next selection rule supported here by FMO method? When this rotatory motion is there. Now here this rotatory motion, its symmetry is there, M symmetry is there, and reaction is photochemically allowed. Reaction is photochemically allowed. So these selection rules are well noted here. See what type of question asked on this topic. With the help of FMO method, the question they may ask on this topic. With the help of FMO method, predict whether by photochemical mode of activation the reaction or conversion of 1,3-butadiene to cyclobutene is allowed by conrotatory motion or disrotatory motion. Allowed conrotatory motion or disrotatory motion. Or they may change the question. With the help of FMO method, predict whether by photochemical activation the reaction is allowed thermally, or reaction is allowed by conrotatory motion or disrotatory motion. But here, when foreign bi-electron system by conrotatory motion, this C2 symmetry we have to consider, and system is allowed thermally. And here by disrotatory motion, M symmetry we have to consider, and system allowed photochemically. Okay. In the similar manner, we can write for 4n plus 2 pi electron system. Okay. 4n plus 2 pi electron system. Okay. So in general, take an example for 4n plus 2 pi electron system. General example is a 135 hexatriene. 135 hexatriene to 13 cyclohexadiene. So this is an example we have taken here. 135 hexatriene to 13 cyclohexadiene. Now what is our next step? Next step is to draw the orbitals of open chain compound. Orbitals of open chain partner. Which is open chain partner? So this is open chain partner. So it contains 6 pi electron. So 6 orbitals are there. Psi 3 star, Psi 4, sorry, Psi 3, Psi 4 star, Psi 5 star, and Psi 6 star. Now draw these orbitals: Psi 1, Psi 2, Psi 3, Psi 4 star, Psi 5 star, and psi6 star. So 6 orbitals we have to consider here. Now psi1, 6 atomic orbitals. Similarly draw as we draw in the correlation diagram method. Psi3 for psi3, 6 atomic orbitals, 6 molecular orbitals. So all these orbitals shown in the similar manner. So orbital drawing must be important while understanding all these. 3, 4, 5. This one 6. 6 atomic orbitals, 6 molecular orbitals. Okay, so give nodes here 1, 2, 3, 4, 5. Number of nodes 0, number of nodes 1 placed here, number of nodes 2 placed in this manner, 3 nodes 2 and this centrally placed, 4 nodes 1, 2, 3 and 4 and 5 nodes 2, 3, 4 and 5. Give the signs plus, 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 then minus, 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 minus. Here in the similar manner, plus, 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 node minus, 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 plus, plus, plus. After node changes to minus, minus, minus. Here plus, after node it becomes minus, 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 minus. Node again sign changes, minus. Here sign changes, plus, 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 plus. Due to node sign changes, plus. Again after node it changes to minus sign. Okay, so signs are here. Here plus, again plus, here plus, due to node changes to minus. Here minus, due to node changes to plus. Here plus, again node, so minus, minus. Here again node, so plus. Okay, here plus, after node minus, after node plus, no node plus, node minus, again node minus changes to plus. So minus, node it becomes plus, after node it becomes minus, minus remains because no node there is. So after node plus, again minus. Here plus, node minus, plus, minus, plus, minus, minus, plus, minus, plus, minus, plus. So these are node and node we have drawn. Now symmetries we have to draw. So symmetries, here you know that it is EM symmetric, it is C2 symmetric, EM symmetric, C2 symmetric, here EM symmetric and C2 symmetric. Okay, EM symmetry, C2 symmetries are there. So these are the symmetry drawing. Now the total number of electrons 6. 2 electrons here, 2, 6 electrons are drawn in this manner. Now these are empty orbitals. These 3 are empty orbitals. We have to decide HOMO and LUMO now. So which is HOMO? Highest occupied molecular orbital, and this is lowest unoccupied molecular orbital by thermal mode of activation. Thermal mode of activation. Thermal mode of activation. So this is HOMO we have considered. Now the next step, that is symmetry of HOMO and by photochemical mode, that we will discuss in the next lecture. So up to this practice for the orbital drawing, it is important. If you draw the orbital and able to assign the symmetries properly, then it is easy to analyze the reaction by either correlation diagram or either frontier molecular orbital. So practice of this drawing the molecular orbital is important. Okay, thank you. Next we will be continuing the another lecture.